So, good morning. In the last lecture on inverse function theorem, we completed the proof of the main theorem. And during this process, we introduced a function, and to facilitate the use of fixed point theorem. And we postponed discussion on this function at that stage because it would have affected the main flow of the proof of the theorem. But it is worthwhile to have a look at this function. So the objective of this talk is to analyze this function, if possible geometrically, get a feel for the function, and then also look at some examples which highlight certain aspects of the inverse function theorem or the conditions that are used in the inverse function theorem. Okay, so first let us start with this what is called the fixed point function. Let me call it the fixed point function for convenience. So recall that we defined it as follows. So we had so the problem was this: you had E open in Rn and F was a map from E to Rn. F was assumed to be C1 function on E. Then we assumed that A belongs to E, where F derivative of A is invertible. Recall so it's an invertible linear operator. That was the assumption that we made. So we designated this so A inverse exists. Now we introduced a fixed point function related to A. What was that? We defined it as phi x equal to U. U was an open set that was defined from that, and we had phi x defined by x plus A inverse this was a definition. Well, if you look at this, x belongs to U and y belongs to Rn, fx belongs to Rn, therefore y minus fx belongs to Rn. So that is y minus is in the range of that is is in the range space. Therefore, what do you have? Y minus fx belongs to the range space, and A inverse is defined because A is an invertible operator. So A inverse is a linear transformation from Rn to R. Okay. Therefore, A inverse of y minus fx belongs to Rn, the domain space. So I am going to distinguish the two spaces, the domain and the range. And then see, this is in Rn, this is also in Rn. Therefore, what you have, this is in the domain. Therefore, phi x is a map from, so phi is consequently a map so for x belonging to the domain space, you have phi of x in the domain space. So phi is a map from Rn to Rn, which is the domain space. Okay, let us look at this map. Let me rewrite the whole thing. If I rewrite this, this is what it is. A of now, it's better to understand this. I mean, we will look at the higher dimensional space soon and what is the picture that it presents. Now, we will look at the scenario. This is the domain space. Let's take one dimension. That is n equal to. Now, let us assume, okay, let us consider the graph. That means this is actually that is the set of points x okay. Now let me draw this. So let the graph be given by something like this. Something like this. Or possibly even something. So this is the domain. This is your E. And this is R. So from R to R. This is generally the point. Now see, A is some point here. And at AFA, we have the tangent, and we have assumed that, okay, so this is the slope. F derivative. F derivative is a number in this case. Okay. So F derivative of A, which belongs to LR, is an element of R. Therefore, you have a line with a tangent with a slope. The tangent line at AFA has slope F dash. Okay. Now what do? We take a point xfx. Now what we do is we draw a line through this point xfx with slope f dash a. So what is that? That is going to be a line parallel to it. These two lines are parallel. Again, so let us write it up. So if x, y y minus fx equal to, equation is y minus fx equal to f derivative of a so it just the point x fx sorry okay, the point x fx lies on this line. This is a line. Yeah, we have already written it. Now you see, choose a y then we find phi of x, okay, as the point, as the such that phi x y belongs to line. Okay, so let me write down the line L defined by this. So what does that give? That gives, see, you insist on this one, on this. So you get y minus fx equal to so given y, you find the point phi x, okay, such that y phi x or phi x y lies on this particular line. Okay, now let us look at geometrically what this means. Something like this. So this is the line, slope f dash a, it's a tangent there. Now what we are taking up is a point x is chosen, this particular line L is this, passing through the point and having slope the same as this line. This is the line that we are looking at. This is parallel to this. These two lines are with a slope A. Now we want to find out phi x. How do you do that? Take a y and corresponding to y there is a phi x. What is that? So you walk parallel to the x-axis until you meet this line L, and then find out the x coordinate of that. This is what you call phi x. So essentially the process is start from x, go to xfx, then go to the range space. So you go like this, I'll mark it, then reach the phi y that you have chosen, go parallel until you meet the line L, and from there you find out the x coordinate of that space. So this is your phi x. So what you are doing is, through this process you are defining a map on the domain space. This is your phi map. Okay. So once you fix y, there is a corresponding map. How do you pick that map? For an arbitrary x, suppose your x is somewhere here, you get to xfx, draw the line passing through xfx with slope f dash a, and then from there you go to the corresponding fx, go upwards to y, and then so on. Similarly, if you were to on this side, there also the same story. Okay. right? But always you will be drawing a line from x fx. X fx is a flexible point. So this gives, so you can easily see that when x is varied, the image point under phi also varies. We are holding y fixed. Okay. So the image point also varies. Now we make an observation. What is the observation that you make? Look at this map, phi. What is the property of, when is, for which point, for which x, phi x is equal to x? This happens when fx moves to y. When fx moves to y, see, you will be coming up to this point and then the line parallel to this. Okay. This line would move there, and so what happens is, when your x moves to y, so your x will be moving here and the corresponding phi x will be moving here. Therefore, x is a fixed point of y. If and only if phi x equal to x. So when phi x equal to x, you see that y is equal to fx, or y equal to fx means phi x equal to x, because this is a well defined operator. Okay. So you get this from the analytic expression, but geometry tells that, see, when you move along this curve, the x will be moving in this direction. Simultaneously, what will happen to phi x? Phi x will be moving in this direction. So when x moves in this direction, phi x will be moving in this direction, because you are always through the point x fx, you are considering a line with slope f dash a. So this is the geometric picture of this operator of this map phi. Okay. So we are actually searching for the fixed point of this map phi, and that happens when y is equal to fx. That is the observation that we make, and this we make use of in our analysis. Okay. Right. Now we will look at the higher dimensional representation of this, because that is interesting. We can draw similar picture, etc. Work with that. So we draw the picture in R2, but essentially for Rn. So we draw the picture for n equal to 2. But that essentially tells you what it is. So you can't draw the graph anymore, but maybe one can give the picture. So what you have? So the situation is this. Okay. So you have two copies of Rn. This is your E. And this is you are taking a map from there to Rn. These are the coordinate systems that you have. Okay. So if it is R2, you have the first variable and second variable. So if it is Rn, you are considering this as the coordinate system that you have. And what you have is from E, so you have a point A. FA with F dash A invertible. Here the invertibility is coming from F dash A not equal to 0. Okay, by which you mean you are not at this point. A is not this point. AFA is not this point where this tangent becomes parallel to the x-axis. Okay, and we are assuming that this is an invertible operator. Now what do we have? I can take A closer to this. So this is the vector. Now you take an x and this vector is mapped by F to, so this is the vector Fx. So you have the two vectors. The vector x, which is mapped by Fx. That's the vector. Now what do we have? You have this situation. Fix a y. Okay. So fix a y here. Fix a y here, and then what about y minus fx? Y minus fx will be something like this. See, you have to consider this as the diagonal of a parallelogram. Actually this vector, but strictly speaking this vector. This is y minus fx. So that this is your y, this is fx. So fx plus y minus fx is equal to y. That's the vector. Now what do you have? It is in Rn. So you can map it backward by A inverse, because A inverse operates on the entire Rn here. It pulls it back. Say it pulls back to some point, say, I mean, you don't know what it is. I'll just mark it here. Y minus fx. Okay. Now what do I call phi x phi x is, see, phi x has the property that phi x minus x is f inverse of a, or a inverse multiplying y minus fx. So that we have got. So what you are doing is, if you look at the earlier definition, what you have y is equal to, phi x is equal to okay. So you have x plus a inverse of y minus fx. So what is it? Complete the parallelogram. This is the vector phi of x plus a inverse of y minus fx is equal to phi x. So that is phi x. So you see, the map that you have in the domain E is probably from here to here. This is the phi map. And mark it with a different color. So this is your phi map. Okay. Now let us see what is happening. You see that as fx moves to y, what happens? This vector moves to y. Y is something that we have fixed. When this moves to phi, what happens is, you see that this will completely reduce to this line. Okay, right? Y is equal to fx. So y minus fx will become 0. So that means y minus fx will be in that case 0. That is y equal to fx. In that case, what happens is, the image of this a inverse of y minus fx will become 0. And 0 plus x, okay, 0 plus x will be phi x. So phi x will be x itself. Okay. So y minus fx equal to 0. Or x is a fixed point of phi. Now this is the structure of the map. Okay. So this gives the or you get phi x equal to x. This is what we have proved, and this is the structure of the map. Now it doesn't mean, I mean, what I have drawn here doesn't mean that this is always a vector inside this region or something like that. See, all this will depend on where you choose your y. Okay. So the explicit choice of y makes the phi. So corresponding to each choice of y, there is a phi. Okay. Now suppose we choose a y which is at fx, then you are going to get x phi x equal to x, as you can easily see. When this one shrinks to 0, this also shrinks to 0. This is the fixed point map, and we have used this fixed point map, and then we have later proved that if we choose the domain appropriately, okay, then we have shown that using this map we have computed everything. Okay, so now you can go back to the proof of the theorem and see how this gets applied. So that's just the structure of the phi map. Now what I want to do is look at some examples. First example, so it makes a remark, okay, it is related to a remark that so the first remark that we make is that the map F is that means there exists a neighborhood from which, that is, there exists A, where we assume f derivative of A is invertible, say U, and Fu such that U and Fu are open and F is 1 to 1 from Fu. This is the statement that we have made. So it is locally 1 to 1. Okay. However, one cannot assert that it is in the linear case. Suppose F is a linear map with F dash A invertible, then you see that F is a 1-to-1 map from Rn to Rn. Okay. So recall, so this is something that we call invertible for Rn, some A belonging to Rn, then F is 1 to 1 on to R. And F dash A becomes essentially F dash X for every X. That is the reason for that. However, this is not true when F is nonlinear. For instance, if you take in the one-dimensional case, if you take a monotonically increasing function, strictly increasing function, then of course this result would be true. But in general, this is only a local phenomena. What we are able to prove is only a locally valid theorem in some neighborhood of the point A. Okay. See, now we want to, this example, substantiate the above assertion. So let us consider the example. Now let us set up the example. The example is this. This is, we have so defined by so what you have is this x, y, this is the map that you have. Okay, so F where f1 of xy e to the power x cos y now this is defined for the entire R2, okay, but what about the range? Now range of is, what do you have? So this is the x-axis, this is y-axis, this is so you have x equal to f1 xy y equal to f2xy. Now this is what you have. So you see that 0, 0 gets mapped to the point, what is it? E to the power 0, cos y is 0, so it is actually goes to 1, 0. So this point moves over to 1, 0. You see that there exists no point in the xy plane which gets mapped to the point 0, 0. Therefore, the range for all other points you can find a corresponding choice of x and y, sometimes more than one choice. Okay, so this is the situation that we encounter. Let me just pick up this picture. So you immediately see that 0, 0 has no pre-image. That is, for no choice of zero. Therefore, the range of whereas all other points you can find one. The given point. Sometimes more than one point has this property. Okay. In fact, you also observe that f of x plus x comma that means the mapping is not 1 to 1 although what about f dash? If you take f derivative of x, y and this is equal to dy, which is equal to what you have? You have e to the power x cos y cos y. This is what you have, and you see that this is invertible. Because which is equal to determinant of what is called f prime equal to e to the power 2x not equal to 0, which is never equal to 0. Therefore, this is always invertible. So, f dash is invertible for every x. So, in this example, what happens is this: f dash is invertible for every x and y however this is the point that I wanted to make, and that's what we have mentioned earlier. Now, if you want, you can work out the local inverse. The local inverse would work out to be, you see that you have got say square equal to e to the power 2x and f1 by f2 so you have, if you take f1 by f2 by definition, see, you see that it is okay. Therefore, locally and tan inverse this is locally, wherever you can invert it. So this is what you get. Now one can actually verify that. Okay, let us see what this map is all about. This is y-axis. Etc. Okay. Now you see that this whole part gets mapped to R2. And every one of this strip will to n plus 2 pi is mapped to now you see that every vertical line namely x equal to constant gets mapped to a circle. At the origin. What happens to this circle is that, see, it just goes round and round, okay, whose radius is e to the power x. So as x tends to, as the unit circle you get when x equal to 0, okay, and then all the circles which center at origin inside the unit circle will be concentric circles, will be obtained for values of x from minus infinity to 0. From 0 to infinity you get all the other circles. Now this is the map. Likewise, every line parallel to the x-axis that is y equal to constant is a radial line. We'll draw the picture. Radial line. This is the radial line that you have, and every vertical line goes to a circle. So this is the picture that emerges. That is the mapping. That is what the mapping is all about. Okay. Now we take up another example, second example, where we show that the following. We have had an assumption that f dash or f is a C1 map. We call that. Next example. In the statement of the theorem, I mean the inverse function theorem, we assume that this cannot be conclusion of the theorem. Okay, so let us consider the following example. We shall consider that is f from define to be equal to t plus two t square you know that this function is highly oscillating type, so it's something see this, so okay, so this sine 1 by t For instance, let us look at this function. So graph of see, this is something like this. So you see that the function that we are considering is something that oscillates. And similar, of course, on this side also you have a similar picture. So there is a rapid oscillation in the neighborhood of 0. This is what you have. So this actually prepares the, so this is the graph of 2t square t . This is the function. So it has a rapid oscillation in the neighborhood of 0. This is the picture that you get, right? Now the given function is actually t plus ft is equal to this plus say gt equal to t. So the sum of two functions. So if we were to draw the graph of this function ft, this is the line t. So what you are having is something like this. This is actually, I have drawn t plus 2t square and t minus 2t square, and what I have is here, and similarly this is the graph of the function. Okay, so it oscillates rapidly here. So this is the graph of TFT. Now we will work out the this is easy to see because this is equal to, but okay, what about f derivative t not equal to 0 is differentiate given by what is it? Minus minus uh, two into cos 1 by t. Okay, and you see that this limit t tending to 0 this does not exist. Okay, why it does not exist? Because this term is oscillatory. And as t tends to 0, this does not tend to a limit. All other terms are well behaved. Okay, so this doesn't happen. Therefore, f dash t is not continuous at t equal to 0, although it exists for all t. Okay, it's not a continuous function, and it's because of the rapid oscillation that you have. You see that in any neighborhood of 0, f fails to be okay. So this shows that the condition that f dash, the continuity of f dash is equally important in the assertion of the or in getting the result in the inverse function theorem valid. Okay, this is because why it is not so. See, you take any neighborhood here, okay, and then look at see if you take a particular value here or here, you see that there are several values of x for which the function takes that value because of the oscillation, the rapid oscillation. It oscillates many times within a small delta neighborhood of that, and that because of that there is no, this is because f oscillates rapidly as So I think that these examples are highlighting certain aspects of the theorem. I think with that, I think we will conclude today's lecture. Maybe we will take it up further in the next lecture. And probably in my next lecture, I will do one more example, which is very fascinating. I am still working on that example and I will do this. Okay. Thank you very much.